Hello friends, today in this video lecture series I'll be talking about Allen-Miller-Trippett rearrangement. It's a organic name reaction video series or a playlist you can watch on this channel. By the way, if you haven't subscribed yet, please subscribe and share this channel with your friends. Alright, let's start with the definition or the introduction of this name reaction, that is Allen-Miller-Trippett rearrangement. This reaction is a ring enlargement of cyclic phosphonium salts obtained by alkylation or acylation of cyclic phosphines in the presence of base. So from the definition or from the introduction, you can see that we need a phosphonium salt, we need an alkylation reagent or acylation reagent, and we need a cyclic phosphine and a base. So these are the key things which we require in order to carry out this sort of rearrangement. We need a cyclic phosphine, a phosphine which contain a cyclic group or cyclic ring, and we need an acylation, and we need a phosphonium salt. It's a Wittig reagent type reaction, but not similar to that. Wittig reaction is a different one, but the only common thing is phosphonium salt here in the Wittig reagent also. Alright, so what is the reaction? This reaction takes place between the cyclic phosphonium. This is the reaction which I am going to put it in a box. So this is our reaction, which we will discuss the mechanism of this reaction in moments. So this one is our reagent. This is a phosphorus and it's a cyclic ring. It's a 5-member cyclic ring, and these are methyl groups. And this R could be anything. It could be alkyl chain, phenyl ring, or cyclic compound. And this is the acylation reagent. This is acid chloride, and this reaction occurs in the presence of water and at the reflux conditions, and you get a 6-member ring, phosphorus being oxidized with double bond oxygen. So this is the conversion of phosphorus from P into P double bond oxygen O, and you have an alcohol here, this one OH, and you can substitute here with phenyl or alkyl ring depending upon what you are using here. You can replace this hydrogen with this ring, and you can replace the ring from 5-member to, so if you start with a 5-member ring, you will end up at 6-member ring. Alright, and the next is if you start from P, you will end at P double bond O, and these are the key conversions. And third addition you will get is OH group in the product side. So these are the key 3 things you get in the product side: 6-member ring, phosphorus double bond oxygen, alcohol, and a substitution. And this depends upon what kind of reagent you are using. Alright, this looks tricky, isn't it? Because how this 5-member ring is going to transform itself into 6-member ring under such simple conditions. So that was proposed by first time Allen-Miller-Trippett rearrangement. So these 3 people proposed this rearrangement. Let's have a look at the mechanism. Now if you are an organic chemist, you will not try to memorize any mechanism. Okay, I have written mechanism here early on, but the reason why I have already written mechanism here just to save the time and make the video shorter. Alright, otherwise I could have started from this ring and then pointed out the arrows, and the video become long and may become a boring. So in order to avoid the time length, I have drawn already the mechanism of this reaction. But let me give you the trick, or let me give you the rule for in order to writing mechanism. Rule number 1 is do not memorize the reaction mechanism. You can never do it. Alright, then what's the solution of that if you can't memorize the mechanism? There's a simple solution. Try to use your simple chemistry. That is, you need to use 4 things: electrophile, nucleophile, acid, and base. Alright, apply these 4 things whenever you try to write down the curly arrows, or when you ever try to propose a mechanism. No mechanism is a final, every mechanism is a proposed mechanism, so based on the chemistry. Like phosphorus contains free unpaired electron. It belongs to the nitrogen group family, so it can act as a nucleophile. And this carbonyl group of acid chloride is well-known electrophilic center, so this lone pair will attack on this, and this bond will break in the favor of oxygen, and it will revert back, and this chlorine is a super cool leaving group, and this will leave, in the presence of a base, that is triethylamine, and you will get this acylation at phosphorus. Now this is acylation. Acyl group is being added here. As you can see here, I am pointing out this acyl group. So this is called acylation step of this reaction, where you have a acyl group. Now phosphorus is making 4 bonds. Phosphorus can make 5 bonds, but here it's making 4 bonds, so that's why it carries a positive charge. Phosphorus is stable when it makes 3 bonds or 5 bonds. Alright, what happens next? Water and reflux conditions are used. So water comes, and as you know that water can act as a base, act as an acid, or act as a nucleophile. Here in this reaction, water is acting as a nucleophile. Now the lone pair of oxygen are attacking on the phosphorus, because phosphorus now is clearly is electrophile because it carries a positive charge. If you don't remember what is electrophile and nucleophile, let me quickly tell you. Electrophile is something which is electron deficient or carries a positive charge, and nucleophile is something which is electron rich or carries a negative charge or unpaired electrons. So oxygen has unpaired electrons. It attacks on the phosphorus and makes a bond between phosphorus and oxygen, this one, and this is the rearrangement step. This bond breaks in the favor of phosphorus because the bond between phosphorus and oxygen is stable, and that's why this bond breaks in the favor of phosphorus. Now this bond, or this lone pair, takes on the carbonyl carbon of this acyl group. Again, this is electrophilic center, and this leaves, and this is the proton of water which is being picked by this oxygen, and this oxygen is converted into OH, and this is the phenyl which was started from this acyl group, and this is how you get a phosphorus double bond oxygen. As I promised in the start, you will get 6-member ring, phosphorus double bond oxygen, and OH, and this was the mechanism of this reaction. I have little space left in this page, so I have cited one example of this reaction which has been published in Journal of Chemical Society organic section, and it's a very old reaction, and you might not be familiar with this name reaction, but it's super cool reaction for transformation of 5-member ring into 6 and phosphorus into double bond oxygen phosphorus and insertion of alcohol. I hope you like this video. For more amazing videos, keep watching this channel and don't forget to subscribe. See you, bye.